Hi guys, welcome back. So I am doing another flashcards video for you today, and you can see my other flashcard videos for more information, but today we are going to be doing special relativity, and as you can see this is a really short section, so this should be a really short video. And there'll be a link below to a PDF of these, and I hope you find this helpful, and let's get started. Alright, so first is conserved versus invariant. So conserved means that it's the same before and after, and invariant means it's the same in every reference frame. So those are two different definitions. The Lorentz position transformation in one dimension. So this is that x prime equals gamma times x minus vt, where gamma is the Lorentz factor. The invariant interval. This is delta x squared equals delta x to the mu dot delta x to the mu. And the value of this will tell you different things. So if it's greater than 0, it's time-like. If it's less than 0, it's space-like. And if it's equal to 0, then it is light-like, or also known as null. Time dilation. This says that delta t equals gamma delta t prime for a fixed x prime. And so again, gamma is your Lorentz factor, and what this means is that moving clocks run slower by a factor of gamma. The Lorentz transformation matrix. So this says if you have the x vector primed, it equals the Lorentz transformation matrix times the unprimed x vector. And basically the matrix is 4 by 4, and it is gamma, negative gamma beta, 0, 0, negative gamma beta, gamma, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, where beta is equal to v over c. It's a lot harder to say than it is to write. All right, the Einstein velocity addition rule. If you have two velocities v and u, and you want to get the resulting velocity w, then w equals v plus u over 1 plus vu over c squared. Things are weirder in special relativity. You can't just add together the velocities. The 4 vector. So this is x to the mu, and it is basically x0, x1, x2, x3, also known as ct, xyz. So basically ct is the speed of light times time, and so it brings time into your position vector. The square of energy momentum for a 4 vector, p squared equals m squared c squared. Length contraction. L prime equals gamma L for a fixed t. So this means that moving objects are shortened by a factor of gamma. All right, Lorentz time transformation in one dimension. So it says that t prime equals gamma times t minus v over c squared x. It's a little bit more complicated. The energy momentum 4 vector. This is p to the mu. I say to the mu. It's not. It's a notation thing. Not anyway. And this is equal to e over c and then the regular momentum vector. Conservation of energy momentum. So this says that the sum of the initial momentum 4 vectors is equal to the sum of the final momentum 4 vectors. Energy in a frame other than the rest frame. So this now you get E equals gamma mc squared, and big T, which is kinetic energy, equals gamma minus 1 times mc squared. Where again, gamma is the Lorentz factor. The relativistic Doppler effect, lambda prime over lambda is equal to the square root of 1 plus beta over 1 minus beta, where beta c equals the relative velocity between the source and the receiver. The relativistic dot product, so a dot b is equal to a0 b0 minus a1 b1 minus a2 b2 minus a3 b3. The Lorentz factor, gamma, we've seen this a lot already, that equals 1 over the square root of 1 minus v squared over c squared. energy momentum formula. This says that E squared equals P squared C squared plus M squared C to the fourth. And lastly, relativistic momentum. P is equal to gamma mv. So again, gamma is Lorentz factor. And that's it for special relativity. So there's a lot of equations, but they're pretty simple. So hopefully you find this helpful. And good luck with your tests, and I'll see you again soon. All right, bye.